Good morning everyone, how are you today?
We are fine, Miss. Thank you. And you?
I'm doing well, thank you. Before we begin our physics lesson, let's write together. Begin. Finish. Now I will take your attendance. When I call your name, raise your hand and say present. Okay? Ali.
Present.
Anna.
Present.
Tony.
Present.
And Danny.
Present.
Clear for class today. Just a quick reminder of our classroom ruler. Number 1, stay focused. And number 2, be active in class. Number 3, respect your classmates and your teacher. Let's do a quick review. We'll remember what we learned last week.
We talk about dynamic fluid that are moving.
Alright, anything else?
The continuity equation. Fluid flowing through pipes with different cross-sectional area will have different velocities, but the volume of fluid flowing through each point in the pipe is the same every second.
The continuity equation, right? Exactly. You got it. Today, we will go deeper into dynamic fluids by learning about Bernoulli principle. Before that, we must know the lesson objective. 2-point lesson objective. The student will be able to explain and to apply Bernoulli principle. This principle says the faster a fluid moves, the lower its pressure becomes. This explains many things like why airplanes can fly, how perfume spray work, and anything. Let's watch a short animation to help you understand this better. Focus on the relationship between speed and pressure.
Thanks to CuriosityStream for sponsoring this video. Watch thousands of documentaries and get access to Nebula for free when you sign up using the link in the description. Bernoulli's equation is a simple but incredibly important equation in physics and engineering that can help us understand a lot about the flow of fluids in the world around us. It essentially describes the relationship between the pressure, velocity, and elevation of a flowing fluid. It has countless applications. We can use it to explain how planes generate lift, or to calculate how fast liquid will drain from a container, for example. We'll explore these applications and a few more later on, but let's start by reviewing the equation itself. It was first published by the Swiss physicist Daniel Bernoulli in 1738, and it looks like this. The equation states that the sum of these three terms remains constant along a streamline. Each of the terms is a pressure. The first term is the static pressure, which is just the pressure P of the fluid. Then we have the dynamic pressure, which is a function of the fluid density, ρ, and velocity, v, and represents the fluid kinetic energy per unit volume. And the last term is the hydrostatic pressure, which is the pressure exerted by the fluid due to gravity. G is gravitational acceleration, and h is the elevation of the fluid, which is just its height above a reference level. This is the pressure form of the equation, but it can also be presented in the head form and the energy form. We can think of Bernoulli's equation as a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. This is really valuable information that can help us analyze a whole range of fluid flow problems. The equation does have a few limitations, which I'll cover later on in the video. But for now, the important thing to note is that it can only be applied along a streamline. We can define a streamline in steady flow as the path traced by a single particle within the fluid. Or more technically, as a curve that at all points is tangent to the particle velocity vector. Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. we want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations, so we can rewrite it like this, with points 1 and 2 both being on the same streamline. There's no significant change in elevation between points 1 and 2, so the potential energy terms cancel each other out. And if we put all of the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible, the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area, A2, is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. This is quite intuitive. By substituting this equation for V2 into Bernoulli's equation, we can see that since the velocity increases between points 1 and 2, the pressure between both points must decrease. This concept that for horizontal flow an increase in fluid velocity must be accompanied by a decrease in pressure is one way of formulating what we call Bernoulli's principle.
So, what did you learn from the video? Anyone?
We learned about the meaning of Bernoulli principle, the formula and application like this.
Let's try a simple demonstration. Take two pieces of paper, hold them vertically in front of your face, about 3 until 4 centimeters. Ready? Now blow strongly between the two pieces of paper. What do you see?
The paper come together, Miss.
Yes, the paper came together. Right, the first air in the middle has lower pressure, so the air on the outside pulls the paper together. That's Bernoulli principle in action. Now think about it. Where do you see? Where do you see example of Bernoulli principle in real life? Okay, have you finished the discussion and the worksheet?
Not yet, Miss.
Not yet. Okay, no worries. You can continue it at home. Before we end, let's summarize. Who can tell me what we learned today? Okay? Anything?
We learned about Bernoulli principle and how it works.
We learn about Bernoulli principle and how it works. Right.
This is summarized from me, the meaning and formula of Bernoulli principle.
Let's close with a short prayer. Let's pray together. Finish. Thank you everyone. See you next time.